guess it's time to kick it off. Hello, everyone. My name is Alex. I've been working on Ethereum for like over 2 years and mostly working on Solidity and working on this other project called eWasm. Have you guys heard about eWasm before? And is everybody familiar with WebAssembly? So why do we have this talk here then? Because this is going to be kind of like an intro to WebAssembly. But we're going to have a lot of questions and opportunity to have questions. So feel free to ask questions anytime. Okay, so today, I think we are kind of like in a Web 2.5 world. We're not in Web 3 yet, but we kind of surpassed Web 2. And what do we do in Web 2.5? Well, we write a smart contract. And in that example, we write it in Solidity. And then we write the presentation layer. And then we write some client-side code. And what do we do with all of these? We have separate deployment processes for all of these different parts. We have to deploy the smart contracts. We have to deploy the rest. And there's a lot of stuff going on there. Who knows what's going on? And I think this could be improved. So probably the goal of Web3, one of the goals of Web3 should be that the developer experience should be much better regarding building dApps. So one concept here, as you can see, is I kind of try to merge all parts into a single page. So one of the problems I think currently with smart contracts is that there's a lot of data representation and a lot of abstraction going into smart contracts. And then the same kind of abstraction and data representation is repeated in the dApp itself. And usually, these two parts are done by separate people. And they may interact with each other, but they probably have a different background because the two systems are so different. So they duplicate a lot of the work. And there needs to be someone else who understands, like an architect who understands all of this and can make the right decisions, where to set the line, what to put where. And that doesn't really work out well today. So if you put all of these into in the same system, you may have a better understanding of what is the bare minimum which should go onto the blockchain. And I don't even mention blockchain here. I just mention consensus. So I think what's important is to know what is the bare minimum of functionality which needs consensus. So in this example, the only part which needs consensus is changing that single line in the database, changing the balances. Everything else doesn't really require consensus. And for example, in Web3, if all of this could be done in the same platform, then probably it's going to be way more seamless on the developer side, and there are going to be a lot more opportunities to optimize it and make it right in the first place. And then we go into WebAssembly, because I think WebAssembly is going to help us to achieve these goals. So what is WebAssembly or Wasm? Well, in short, it's just a binary format for the web. I want to take a step back before we go into the binary format part. So like today and for a lot of years, browsers were able to execute JavaScript. And that's like the only way to write software into the browser and logic into the browser. And then there's this other project called Emscripten, which can translate a lot of different languages into JavaScript. And this works, but it was kind of slow. So there was a next evolutionary step called ASM.js, which, if I wanted to put it short, it's just a set of rules of writing JavaScript patterns, which the VMs can find and can optimize. Have you guys heard about ASM.js before? that's a lot. If you search for awesome login lang, it's going to be a GitHub link. It's the first hit in Google. And you're going to find all supported by all the major browsers. It's been out for over a year. It's been supported well. Earlier this year, it has been enabled, but development has been ongoing for like over 3 years. And we actually looked into WebAssembly early 2016, where it was still in development mode. But over the course of 2016 and 2017, there wasn't too much changing on it. So practically, it's been stable for over like a year and a half. And there are also a lot of independent implementations of WebAssembly outside of browsers. So by that I mean that there are VMs which can be used outside of the browser to run WebAssembly code. So a good example is Node.js. So people can write JavaScript code which works in the browser, but you can also use Node.js to run it outside of the browser. So the same can be applied to WebAssembly. Is this? Okay, it's working now. So like one VM, for example, is called Binarian or Webbit, and there's another one called Wasm, which is a JIT. But there's also a VM written by the Parity folks, which is used in Polkadot and Substrate. It's purely written in Rust. And there's also a VM written in Go, which can be used by Go projects to implement Wasm support. So by that, you can see that Wasm isn't really limited to the web. It's highly supported outside of the web already today. Okay, so isn't that kind of like Java? It kind of is and kind of isn't. So Java wasn't designed as a web-first system, language, VM, etc. But mostly because it became before the web was big. And it also is tightly coupled with a single language, which is not the case for WebAssembly. And because of this tight coupling, high-level instructions, for example, instance of, put field, new array, a lot of different instructions to interact with objects. It is instructions to create objects and deal with those. So WebAssembly doesn't have any of these. It's way more low-level than what Java is doing. But WebAssembly could turn into Java. And by that I mean WebAssembly is designed to be flexible and extensible. So WebAssembly, the bytecode format itself, if I go a tiny bit more technical here, the bytecode format itself is built up of sections. And different sections can define different parts and data. And there can be custom sections added outside of the core WebAssembly, which still makes it valid WebAssembly bytecode. And these custom sections can define things like abstractions of higher level objects, which then could be kind of understood within a WebAssembly context. And there's some plans and proposals by people to have abstractions for garbage collection. So are you familiar with garbage collection? So practically a lot of languages decide that developers have to manage memory sections and objects themselves. They have to allocate them, and they have to delete them. But many other languages decided that developers shouldn't do that at all, so they should just randomly create objects, and the language will deal with the removal and the allocation of that for them. And to do that, many languages have a garbage collection system, which means at some interval, somehow the language will decide, okay, this stuff isn't needed anymore, and we can remove it. WebAssembly, because it's so low level, it doesn't have any kind of notion of objects and any kind of support for garbage collection. But it doesn't mean that you cannot compile a language which uses such a system to WebAssembly. So what happens today, if you compile such a language, is that all of this supporting code, which does object management and garbage collection, is compiled into the output. So as a single example, if one compiles Go, the hello world turns out to be 1 megabyte in WebAssembly from Go. And the main reason for that is it just pulls in all this standard library to do garbage collection and object management, etc. And the idea here is that WebAssembly could have this extension in the future and do this for you. And the result is that the bytecode will be smaller because all this like helper functions for garbage collection going to be supported on the outside. But this is all flexibility, and it's not there yet. And if it's going to be introduced, it's going to be optional. Okay, the EVM. Everybody knows the EVM, right? So the EVM was designed in a very different mindset than any of these previously talked about VMs. It is really cryptography oriented, and it doesn't at all model a regular computer. And it is slow because of all of these points, probably. But there are two main reasons I always mention why I think it's kind of slow. Because it's cryptography oriented, it is also 256-bit focused. So it is a stack VM. All of the items on the stack are 256-bit wide. And that also means that all of the operations on those items have to deal with all of this precision. All of the calculations have to take all of this precision into account. And in many cases, you don't need that precision, but it is done nonetheless. There's a lot of extra work done there which doesn't need to be done. And it also mixes a lot of high and low level functions. So just like the JVM has these like high level instance of functions, the EVM has also a couple of high level functions which may not be the best to be there. So one example is this catch256 hashing method, which is part of the EVM. That's quite high level. But it does have this one giant benefit. It is tiny. It is kind of easy to implement and fully comprehend. How many of you guys know the entire EVM instruction set here? Yeah, and how many of you guys would you know any other instruction set, you know, to that extent as you know EVM? Yeah, nobody. Nobody, because everything else is much, much bigger. So WASM is also a bigger instruction set compared to EVM. So that's one of the main benefits of EVM, and that's one of what a lot of people start with, that it's tiny, it's easy to implement and comprehend. But it's kind of also not well optimized for performance. So the next point here is EWASM. As I mentioned, I've been working on EWASM for a while, and what EWASM is trying to do is to marry WebAssembly with Ethereum. So basically, we're building on the extensibility of WASM. And by that, I mean we're not changing WASM at all. We don't need to change it. We just take it as it is. But we can extend it to expose all the Ethereum state into WASM contracts. And even though we don't extend it, we still have to strictly verify it. And we have to remove all the opportunities for non-determinism in WASM bytecode. So WASM itself does support floating point numbers. And that wouldn't necessarily mean that it's non-deterministic, but there's one single decision in WASM for optimization purposes that it doesn't restrict the way not a number is represented in floating point. So we just decided that we disallow any kind of code which uses floating point, because there's not much need today for floating point in smart contracts. The way we do this, whenever a smart contract is deployed to the network, we do a verification step. And if your contract contains any code which is not allowed in the blockchain context, it is just rejected. But it's still standard WebAssembly bytecode. You don't need any special tool to produce that bytecode. And then we have this magical process called metering. Should I go into that? Are you guys familiar with the EVM metering? So in EVM, metering happens fully at runtime. Whenever an instruction is executed, it needs to charge for the cost of that instructions. And instructions can have multiple costs. Many of them have a base cost, just for representing the computational cost it has. But many of them do touch, the Ethereum state. They create data structures, or they read from data structures. They call up external contracts. They create contracts, etc. And all of those are way more costly. And many instructions then also have like variable number of arguments, or they may like read 4 bytes, they may read 40 bytes, and you need to charge accordingly. So all of this is happening runtime. And in eWasm, we try to change that, and we don't do it at runtime. So we have split these costs into two parts. There's a computational cost, and then there's like the state accessing cost dimension. So the computational cost, we can calculate all of that up front before executing the code. So the way we do that is we look up the bytecode, and we look up distinct instructional blocks. So by that I mean any block which doesn't have a jump, and is, say, not a jump destination if we talk EVM terms. So anything which will interruptedly be executed is a distinct block. And we can calculate how much that given block going to cost in total. So one example is, if we stay in EVM, say push, push, add, jump, then push, push, and add is one single block. And we can calculate the cost of all those. And we insert a extra instruction in front of them called use gas, and say 3, if we assume that push and gas each cost 1. And we have to do that for each of these blocks. So in practice, that's what we do in Wasm. We select all of these blocks, we calculate how much each of these blocks is going to cost, we insert a single instruction in the beginning of that, and at runtime, only that single charge is added. And then if a special instruction is touching the state, that will be done at the runtime. A question? Yeah, so well, I guess everybody heard it, right? Yeah. So that's the metering is happening at the time of deployment, or say it can also happen before execution, but it is done by the node, and it is done by consensus critical code. So no matter if you added this use gas statement, so one example, if it's implemented in a way that it just takes whatever bytecode is submitted, and say that bytecode can have use gas statements in them, then you are just making yourself to pay way more, because your use gas statement isn't removed, but another one is inserted in front of it. Yeah, the node goes through all of this and inserts them. So with eWasm, the goal, okay, one more question. Yeah, that's a very good question. And so we just split really the computational costs and the state accessing cost. And in EVM, it's not really split, but it's one example, say the store instruction. The store instruction, we have just taken the cost of the store instruction, and that's like the state accessing cost of it. And that matches 1 by 1. But obviously all the arithmetic opcodes, they don't match one-on-one to Wasm. And there's no intention to make them match one-on-one, because Wasm likely going to be executed much faster. So all of these tiny instructions in Wasm should cost less than the appropriate EVM instruction. So it's one final example to that. In Wasm, there's no add 256-bit instruction. There's only add 64-bit instruction. And the appropriate one in EVM is the add 256. So that would be like, say, 4 instructions at least in Wasm. So the appropriate cost in Wasm should be at least 4 times less for that. You with the glasses. So that's a really good question. How do we determine the actual gas cost? So the gas costs right now are determined based on the latency of the instructions, which comes from so basically because the target is traditional computers, we have looked at the Intel manuals and we have looked at the ARM manuals. And we looked at all of these instructions and identified how the WebAssembly instructions would map to those machine instructions, and looked at the actual, latency by the specification. And by that we have arrived at a relation between those instructions. And the second step to that is then doing benchmarking and figuring out, say, the cost of addition. And from that we can, calculate everything else. And as a final step, we then also need to do benchmarking again to see if any of these assumptions were wrong or correct. If I hope that answers it. Yeah, I would be glad to have a discussion with you. Yeah, that's a very good question, whether benchmarking is really dependent on the VM implementation. And that's true. And therefore, we're looking at benchmarking on, if possible, all of the VM implementations today, but at least different categories of VM implementations. So we have interpreters written in C and Rust, and we have ahead-of-time compilers written in C using LLVM, and we have these like hybrid JITs in the browsers, which can do a variety of things. And we are trying to benchmark them on all of these different systems to arrive at some kind of agreement. Yeah, so that example, I tried to explain it in terms of, because I didn't have the slides here, so I tried to explain it in terms of EVM. But in WASM, it's kind of different. It's not entirely like stack-based, and there's no like jump destinations, and there's validation in WASM, and it cannot really jump to any random location. It cannot, yeah. Yeah, yeah, yeah. Okay, if no other questions, I'm just gonna go through this, and then we can have, a lot more questions. So with the WASM itself, the goal is to introduce it on the mainnet. And the first step to that is we're launching a testnet. And then probably introducing it, like as a hard function on the mainnet is quite a big feat. So we're looking into like a more, step-by-step approach. And one possible first step to that is introducing for a specific set of contracts these so-called precompiles. Are you familiar with precompiles? Yeah, so there's a lot of requests in the community to introduce new precompiles, and we could make that much more easier if we would have this WASM as like a baseline to allow new precompiles to be added to Ethereum. So, we already done. Yeah, there's not too much there anyway. Yeah, basically, it's not only WASM doing WASM. There's all these other chains. Coven has its own version of eWASM called pWASM, almost compatible, but not entirely. And then, obviously, Substrate uses WASM entirely. And the next step you guys should do is move to Studio 1.0 and join the panel discussion. There you can ask all these questions. Thank you.